So here we are having two wires of same length and same material, but their radius their radii they are in the ratio of 1:2, and they are stretched by unequal forces to produce the equal elongation. And we have to find out what is the ratio of these particular forces. So we know that in this particular case, they are producing the equal elongation, and therefore delta L1 is equal to delta L2. Now we know that delta L is given by PL upon AE. So PL upon AE for wire 1 is equal to PL upon AE for the another wire. Now, as over here they are made up of the same material and their length is also same, so we can say that this length will get cancelled out from both the sides. They are made up of the same material, so modulus of elasticity is also same, so that will also get cancelled from both the sides. So L1 is equal to L2 and E1 is equal to E2. So we are left with only P upon A for first wire is equal to P upon A for the second wire. So P1 upon A1 is equal to P2 upon A2. Now cross-sectional area of the wire is given by pi R1 square, and here also it will be pi R2 square, and we can cancel out this pi from both the sides. So it is P1 upon P2 is equal to R1 square divided by R2 square. Or we can say that P1 upon P2 is equal to R1 upon R2 bracket square. Now here the ratio is given as 1 upon 1:2. So R1 upon R2 is 1 upon 2. Therefore P1 upon P2 is equal to 1 upon 2 square, that is 1 by 4. So the ratio is 1:4 between these two forces. Now suppose in the next example it is given that the length of the wire is increased by 1% when a load of 10 kg is suspended from it. Now if the same load is suspended from the wire of the same material but of double length, so here the length of the another wire is having 2 times the length of the original one, and radius is also double, then we have to find out what is the percentage length that is increased. So for wire 1, suppose we use the given data, that is, it is given that the length is increased, so elongation is 1% of the original length. So this is delta L is equal to 1 upon 100 of the original L. So delta L is PL upon A, so this L will get cancelled from both the sides. So we can say that P upon AE is equal to 1 upon 100, but area is pi r square. So P upon pi r square E is equal to 1 upon 100. So this is the first relation that we have obtained. Now for the second wire, again delta L is equal to PL upon A. The force is same but the length is double, so in place of L we have substituted 2L. Area is pi r square but radius is double, so it is pi into 2r bracket square into E. So this is P into 2L as it is, 2r square, that is 4r square. Now this 2 and 4, so here in the denominator there will be only 2 that will remain. Now the relation that we are obtaining is P upon pi r square E. So this P upon pi r square E. So P upon pi r square E, that term is nothing but 1 upon 100. So that is 1 upon 100, and already L is there and 2 is also there. So it is L upon 200. So we can say that change in length of the second wire is L upon 200, and therefore percentage increase in the length will be equal to delta L upon L into 100. So delta L is L upon 200 and original length of the second wire is 2L. Again this L will get cancelled. So it is 1 upon 400 into 100, that is 0.25%. So this is the percentage increase in the length of the second wire, whose length is double than that of the original length of the wire 1, and radius is also double. Now in the next example we are having a solid circular bar of certain material and it is remaining unchanged in volume when subjected to the uniaxial loading. So it is subjected to the loading in one direction and its volume is not changing. We have to find out what will be the Poisson's ratio of that particular material from this data. Now we know that the volumetric strain is nothing but delta V upon V is equal to linear strain into bracket 1 minus 2 times the Poisson's ratio, that is mu. Now here it is given that the volume is remaining unchanged, so it remains unchanged in volume, so therefore we can say that delta V is 0, so this is 0 upon V is equal to E into bracket 1 minus 2 mu. So we can say that E0 is equal to E into bracket 1 minus 2 mu. Now this linear strain cannot be equal to 0, and therefore we can say that 1 minus 2 mu is equal to 0, or 1 is equal to 2 mu, or you can say that mu is equal to 0.5. So this is the required